Differential equations are at the heart of machine learning. Without them, we couldn't train models effectively. But what exactly do they tell us? They describe how fast and in which direction the values of a function change at a particular point. But what does that really mean? To calculate a derivative, we take the value of the function at a point, then measure it again a tiny step further along. By dividing the difference in function values by the size of the step, we get the rate of change at that point. Imagine a machine producing 2 pills every minute. If you check now, you have a certain number and you know that every minute you'll have 2 more. This is your rate of change. After 10 minutes, you'd have 20 more pills, and so on. Now let's see how this looks as a function. Because it's just a straight line, the rate of change is constant at every point. In this case, the size of the step, h, doesn't matter. But what about more complex functions? Take a quadratic function, for example. Imagine you are growing bacteria that double every minute. Starting from 1 bacterium, after 1 minute you have 2, and after 2 minutes you have 4. Here, the rate of change depends on where you are along the curve. The size of h can affect the calculation. And to find the exact rate of change at a specific point, h must be as small as possible. This is where the concept of limits comes in. The derivative is then expressed with this equation. The exact numbers aren't what's important. What matters is that the derivative tells us how fast the function is changing and in which direction. So, how is this useful for training machine learning models? Imagine a simple model with 2 parameters, x and y, and we want to find the point where this function reaches its minimum. Suppose we start at x equals 0.5 and y equals 1. The derivative with respect to x is 1, and with respect to y is 2. Since we're looking for the minimum, we move 1 step back along x and 2 steps down along y. We end up at x equals negative 0.5, i.e. y equals negative 1. The derivatives point us directly toward the minimum at x equals 0, y equals 0, but if we take too big a step, we can overshoot. That's why, during training, we follow the direction indicated by derivatives in tiny steps, updating the model gradually. This ensures we reach the minimum efficiently and safely.